cell is example 5.1. But the tabs have all sorts of fun things that we'll explore and look at. So let's do this. So what this tab, this is just the data tab. So in fact, let's see why I did this. Yeah, data from the book. And the data from the book backup. I think I just put it in there in case I messed it up. Anyway, let's see. Yeah. So let's see. So the data from the book. So this is simply example 5.1, right? Remember we had 4 different pressures, 3 different temperatures, 2 different days. Days the background. Yeah, days the background. So it creates the blocks. You can also see why they call it that, a blocking factor, right? It makes blocks of data, and each of these are the factors. And again, like I said before, no replication. If we'd had replication, we would have had, 2 values at low, and 2 values at medium, and 2 values at high, something like that. Okay, so the first thing, we won't look at, let's see, we won't look at that yet, because that we'll go back to that. So the first thing is, let's just suppose we loved our real statistics and tried to treat this like a 3-way ANOVA. You know what's going to happen. We're not going to be happy because of that comment I just made. We don't have any replication. So since we don't have any replication, and if we just select it and say, do 3-way ANOVA without thinking, how are we going to get an error, a random error? Unless we do something like we did before, make a surrogate error, but we're not doing that. We just select it and do it. So let's see. We just randomly select it, boom, and just hit, give me my 3-way ANOVA, this is what you get. Once it divides by 0, well, why? Because you didn't have any random error term. There was no way you could calculate random error because we didn't have any replication. So we got a big fat 0. So whenever we tried to make a mean square error here, we went to pot. So don't do that. But at least it's nice to know when that happened, why it happened. You didn't have any replication. You're trying to use something that wants replication. No, you can't do that. So what can we do? All right. Well, we can take that Lincoln paper and we can program it. We can program the. I'll blow it up now. So we can take that Lincoln paper, the one we just went over, make all these calculations. And I've just done them intermediately. Here's the square of every entry in the cell. This is the square of the sum of all the temperature samples. This is the square of the sum of both values, temperature and pressure. Let's see, I get pressure over this way, right? Sum of the square of the temperature over this way, I guess, yeah. Okay, this way. I got the grand mean here. So you can click in there and see what I've done. I've just simply added things up, squared them, sum and squared there. Squared each of those terms. There's the sum of each. So I've implemented each of those equations that you saw in that Lincoln paper. Okay, and then I've gone and made the calculations that they did. Got the degrees of freedom for the blocks, temperature, pressure, the pressure and temperature combination, the error, the total. I got the sum of the square errors. I got the mean square error, right? That divided by that divided by that. I've got the F, right? F is that divided by that, or that divided by that divided by that divided by that. Okay, and then I got the P's. So this should look exactly, if I did things correctly, like table 5.2. Let's see. Yeah. So I should have exactly the same numbers that they did. Yeah, I do. So I've done by hand, using that Lincoln University paper, exactly what Minitab did. So again, I don't think that's that bad. I don't think that this one sheet was all it was, is the work that came in the Minitab thing. So you've actually got a 2-block, 2-factor ANOVA you can use right here. Now, you're right, if you had to, you had to add another, maybe you had different levels, you might have to add a row or a column, but I think you can see what you did. And again, let's see, remember, you can also look at here if you forgot how things are calculated, and just see how you calculated mean square error, that divided by that, or you can look in here and see how you calculated an F, right, which was that divided by that, right, W there divided by that, and then the P, like we discussed before. Now I probably didn't use I didn't use the right tail. I just used 1 minus the F distribution. You know, this whole area is 1, so you can use 1 minus this. Why did I do that? Probably because when I did this sheet, I didn't remember there was a right tail. You know, but that's good to see. So I'll probably do that on all of them, didn't I? Yeah, 1 minus F. So yeah, so again, this is right tail, this is the regular F disc, so 1 minus F disc is going to equal the right tail, either way. So let's see. So I came to the exact same conclusion, right? My conclusions are in yellow. Temperature mattered, pressure mattered, the temperature and pressure does not matter. Same conclusion they did because it's the same math, same in over table, same thing. All right, so now let's see. So you've seen how not to do it. You've seen how to do it using that paper. Let's see. Now what else can we do? Yeah, let's see. What else can we do? Well, one of the things I did, I just did the regression. Remember how you laid out the data, coding it, day, pressure, 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 next pressure, 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 next pressure, pressure, temperature, low, medium, high, low, medium, high, low, medium, high. And here was the sample value, the yield, or whatever it is they're measuring, kilograms. And then do a regression. And so what I'm basically doing is fitting a slope to it, a linear model to it. Now let's see, the regression kind of gave me some conclusions, didn't it? Remember, if the 95% confidence interval on the regression grabbed 0, it was telling you it really didn't matter. It did not matter, so this one doesn't get 0, pressure mattered. This one doesn't include 0, so temperature matters. So we kind of made that same conclusion that we made before. Now, I didn't do the pressure and temperature part of the regression because I didn't make a column for pressure and temperature interactions. But we already knew that. But this is not how I'm going to use this. I'm going to take this day slope here, and I'm going to compensate my data for the day. So rather than, like I'm saying, rather than being a statistics person and just having to use my ANOVA and having, I'm going to say, no, I'm not doing that. I'm going to account for the background variable. Because that was one of the 4 approaches, right? We could not have it, that'd be great. Or we can do all the experiments in one day. We still have it, do them all in one day or one batch. We could do the statistics, or we could account for it. Well, let's account for it. How am I going to do that? Well, one thing, I just copied this data over here. There's nothing, regression 2 is just a copy of that. I just didn't want it to change if I hit the wrong thing. And so now, what I have done over here, I took our regular data. So day 1 data, I didn't do anything to. Day 1, day 1, day 1, day 1. Day 1, 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 day 1. I said, that's our base day. Now let's fix the day 2 data with that slope. So here, this is the day 2 data. This is the day 2 data changed with the slope. What did I do? Well, the slope was 1.7. So each time I just took, there was only 1 day difference. I was assuming. Now it might, if there was 10 days, or I make an assumption. This is 1 day. This is the next day, and so I'm going to say, hey, I'm taking this minus 1.7 since there was 1 day. Got that. That minus 1.7 to get that. That minus 1.6. So I've compensated for this day effect. I've fit a linear model to it. I've linearized it, and I've subtracted out the due day. So I've made, quote unquote, made day 2 look like day 1 with my regression fit. Now I'm doing an ANOVA on that without worrying about blocks. I fixed my data, right? This is all just great data with some replication. It's okay. So what happened? Well, look at this. Okay. I come out with the p-value. Temperature mattered. Pressure mattered. Temperature, pressure did not matter. So I came up with the same statistical conclusion with a different approach. Now, if they were borderline, would this always work? Probably not. If it was right at 0.0499, maybe my regression would come out with it flopping to the other side. You have to understand that because they are different statistical approaches, you might come with a slightly different conclusion if they're borderline. But none of these were. Look at that. I mean, temperature was not near, no borderline on that. Pressure is pretty darn far below, and that was pretty far above. And so that was one way to fix this, a compensation way that I didn't rely on statistics. I'm being an engineer. That's okay. Now let's go back a minute here. Let's see, go back to the correct way. Okay, yeah. So this tab was the Lincoln University paper. This tab is table 5.2. This is the, I shouldn't say correct way. This is the ANOVA, the statistics way. I want you to look at the error number, okay, and I want you to look at the day, some of the square numbers. Okay, so the error, some of the square errors is 9.36. The day is 17.34. What if we did an ANOVA and we didn't know that we had day as a background? Well, remember right at the start of the lecture I said what would happen? That if we just do that, not knowing that day is a background, remember the error for the day is going to plop into the random error. This is going to go into that. Okay, let's do that. Let's do the wrong way. I call it the wrong way. Yeah, wrong way with Excel. So let's just take this data. I just did it. I just blobbed it together. Day 1, day 2, day 1, day 2, day 1, day 2. So I'm acting like day 1 is one replication, day 2 is another. And I'm acting like I have no clue that day matters. So I'm going to do a two-way ANOVA with replication and see what happens. Well, I want you to see what happens. Exactly what we said would happen, right? The random error is 26.7. 9.36 plus 17.34 is 26.7. So, and what happened? Temperature still mattered. Well, yeah, remember temperature was 6 times 10 to the minus 5th before. So temperature still mattered. What? Pressure doesn't matter. Yeah, we screwed up and temperature pressure still doesn't matter. So we goofed up. We goofed up because we couldn't see the effect of pressure because we didn't know that day mattered. So the ANOVA thinks that variation is just due to randomness. Whereas we know it was due to the day. If we know it's due to the day and we do the correct math, we can suck it out, right? We sucked out 17.34 amount of error out of 26.7. We sucked out almost 60% of the error and put it into someplace we knew where it was. If not, no, well, we've done a bad design of experiment. We've thrown that error in here, and now we've missed a conclusion. So you can see the implication of this, and you can see it explicitly mathematically. You know what? And you can see how you can make that mistake, right? Oh yeah, I did my experiment one day, I did it the next. I didn't think day mattered. I just threw it all on the table and did my replications because it took me all day to do the experiments one time, all day to do it the next. Didn't think it was right. Pressure doesn't matter. Well, it might have. But if you hadn't recorded that and you didn't do the analysis, it did matter, didn't it? Let's see. And it was close, right? I mean, I forgot what it came out to be. Let's see. Yeah, it's close in the 1% world, right? It was, 0.009, but in the 5% world, it wasn't close. Let's see, back here on the wrong way, let's see. How far away was it? I don't remember. Yeah, way far. Yeah, it was way far from 0.05. You really lost the pressure in that experiment. So, very, very interesting conclusion, I think. And it seems to make sense and support this blocking, the need to do the blocking, the need to understand where your errors come from, what is a background and what's not.
So when you're looking at, because I could see that would be a common mistake.
I think so too, yeah.
So to prevent that, are you saying we should take our initial results, but maybe block it if necessary?
Yeah.
To make sure that we're not missing something?
Yeah, and how would you know to do that? Well, one of the ways that they are guiding you very simply, just look at the plots. You use your head, they look at the plot and they say, well, look, like on page 111, they got the plots. It looks to me like pressure matters. Right. Now we've got one more little statement to say. You look at page 111 and it's like, yeah, I could see, the one figure looks like the low pressure one kind of goofy, but it doesn't appear to me like that as pressure increases, your yield goes up. And so I would say, look at that plot, it would make me think that pressure matters. And so when I blobbed all the data together and I came up with pressure not mattering, yeah, it made me think, well, maybe I messed it up by not blocking the days. Now remember too, this conclusion, like we said earlier, it tells us at least one of the pressures were different. It didn't say which one. This data kind of makes it look like the high one mainly is the difference. So can we test that? Well, you bet. That's the last little piece here. Let's see. We've got Tucky and Sheffy in our little pocket. Remember the the ways to check a comparison. Yeah, here it is. So let's see. Let's see it back here. Okay, there. Yeah. So why don't we, looking at those graphs, we think that fourth pressure, the 275, looks like it matters, and the others kind of, maybe so, maybe not. So remember that Sheffey technique was a quicker way. Remember Tucky compared everybody to everybody else. The approach that anyone would do. I would do that. A to B, A to C, A to D, B to C. Just go through them all. And remember Tucky, you made that. The Sheffey, you made this weird thing called a contrast that always the coefficients always summed up to 0, and you compare one to some others. So in this case, looking at this graph, if we kind of make the conjecture that, hey, the 200, the 225, and the 250 pressures kind of look the same, and it looks like once you crank it up to 275, we're starting to get a bigger yield. So maybe that 275 one is the big, the break point, the threshold point. Why don't we make a contrast where we compare the mean at the 200, the 225, and the 250 to the 275. So my Sheffey contrast is L is the mean of the 200 plus the mean of the 225 plus the mean of the 250 minus 3 times the mean of the 275. Remember, you had to balance it. The sum of these coefficients had to be 0. Okay, so let's make that contrast. So here's the mean of the 200, mean of the 225, the mean of the 250, 3 times the mean of the 275. So we got this number. And remember what we were doing? We were coming down to form a confidence interval at the end here. And if the confidence interval got 0, it didn't matter if it missed 0, it didn't contain 0, it mattered. So if you remember the Sheffey approach, I know it's a cookbook formula, but it was, you did this contrast. The hat means it's an estimate of the contrast. You got the variance of the contrast. The variance of the contrast was the mean square error, straight out of the table, 5.2, times this thing in brackets, which this thing in brackets comes from, we had 6 total, the sum of the absolute value of the coefficients is 6, and then 1, minus 3, we're squaring them. So this number of the brackets came out to be 2. Just randomly, doesn't always come out to be 2. But and then the mean square error, that was straight from the MSE in table 5.2. Okay. And remember, you're going to have that number because you're not going to do Sheffey unless you've already done an ANOVA to told you that it was different. So you pull that number out. That's the variance of this L. The standard deviation, of course, is the square root of the variance, 1.7, 1.3. And then, let's see, let's do a 95th, let's do a 95% confidence interval. So let's see, I got to get the F. Numerator has 3 degrees of freedom, that's the pressure. The denominator has 11, that's from the error. So we get the F value. Why am I getting the F value? Because remember because the formula for the confidence interval was the L hat plus or minus A times the standard deviation, and this A is a function of this weird F. Remember, this is just that Sheffey, again, it's the Sheffey cookbook formula. So this was the number of pressures minus 1, that's your 95%, that was your number of pressures minus 1, that was your error. So you get the F value, which uses the inverse function. So I get that F value, multiply it by the K minus 1, which is the number of pressures minus 1. There's my little A. And so the Sheffey cookbook says L plus or minus A times the standard deviation gives you an interval. This interval runs from minus 9.7 to minus 1. It does not contain 0. So that tells you that contrast is statistically significant, which tells you that 275 pressure was the one, was for sure different from the others. Okay, so again, it didn't tell you whether 1 was different from 2 or 2 was different from 3, but it did tell you that the 275 was significantly different from the others, which was kind of our conjecture and kind of what we knew from the graph. And if we want to do more, well, we could do Tucky and compare each one of them, or we can make a new contrast and compare 200 to 275 You see how you go on and on, or we can just quit here and say, no, the graphs, we found from the ANOVA that pressure and matter. The graphs looked like 275 was the most significant. Sheffy showed us that it was. No, I'm happy. 275 is my threshold. Let's crank it up to there in our procedure, or at least make it 275 or 300 or whatever, and that's good. So you can see how you can keep going on this. Or we can, like I said, we can do tucking, compare them all, and come out with which ones mattered and which ones didn't. Maybe we don't care, because maybe we don't care whether 225 is different from 200. If we're going to set 275 as our threshold anyway, I don't care. 225 is slightly better. So see how this works. Now you could also, the last little section of the chapter, you could also make this into a Latin square. Remember the Latin square, you had to have had to be a square. You had to have the same number of treatments, the same levels in each factor, and then the background would have to have the same number of levels too. To me, that's starting to get a little bit far-fetched. But you could, if you could control everything. But then often you might get too many. That's the example they show. I think they do a Latin square where they had enough treatments that you're going to have, I forgot, 144 or something ridiculous. And then they asked, is there ways you can cut it back? And one of their conclusions was, yeah, get rid of one of the background variables or cut down the number of levels and something. Well, we know that anyway. So if you were interested, you could do it in a Latin square. But I don't know. I think that, to me, that's getting kind of narrow because of the restrictions on the number of factors and how they had to be equal, and the levels had to be equal. So I hope this makes sense, and I hope this chapter, kind of start consolidate things from the perspective of what does it mean to have a background variable? How can that mess you up if you don't know what you're doing? And maybe it's okay, because maybe the background influence, in this case, the background was 2/3 of the error if we blob it together. Maybe it's not, because maybe it's a weak effect. And maybe it's okay to blob it together, which I'm saying that means the background variable really is not a background variable. But if it is, you see how it can roll into the calculation. It's rolling into this down here, which is killing your sensitivity, which is killing your conclusion. And so you can see how you might not want to do that. You might want to separate things, but you can't do that if you didn't record it, or you didn't understand it from the outset, or you didn't even know it was a background variable. But at least if you recorded it, maybe you could, retroactively take care of things. And then once you did find a difference, you can explore it further with some in-depth comparisons or one of these contrasts like Sheffy, and prove to yourself that that one was the one, or I think that gives me my threshold. Again, it all depends on what your objective is. Was your objective to differentiate between every little level? Was your objective to set a threshold? Was your objective just to understand that pressure matters so that maybe we want less yield? I don't know. Maybe yield is, instead of yield being good, maybe yield is a safety violation being bad. So we want to turn the pressure down or something. We just want to limit. But you can see how the mathematics work. And then the other piece out of this chapter is you can see a couple of things that you don't have to be a slave to Excel's ANOVA or Real Statistics ANOVA or Minitabs ANOVA. It didn't take me long to find that paper. And I don't think the math in that paper is above anyone in this class. It's a couple of sums and squares and lay it out in the table. So even if you got some weird situation, often you can find something to program it yourself. Or even if you don't like that, my little approach of compensating for the day was simple. Dumb. You didn't even have to do a regression. You could have made your own slope just by looking at it. Oh, look, it's like every time, in the days, the yield went up by 1.7. Let me just take that out. Okay. And again, don't do things like that without some physical understanding. But I argue that anyway. Don't be messing around with this kind of stuff without some sort of physical understanding of what's going on, or you will make really bad mistakes. Make conclusions that make no sense. But hopefully nobody's doing that. That's being a bad engineer. Don't run a finite element model without physics understanding. He'll give you an answer. Give you a lot of answers. But so there's different approaches: controlling backgrounds, statistically accounting for it, taking it out, making the comparisons when you get down. So I hope this is starting to solidify, and thinking too. Like I really like doing the two-way ANOVA the wrong way. and seeing the two errors combined into the one. It makes sense. Yeah, look at that. That background error just fell right in there and it messed it up. It messed my conclusion up because I didn't have the precision and sensitivity because I had too much random error because I had a background variable making my random error huge. And so, and it's a long way around to say don't do that. Of course we know not to do that, but sometimes you can't control it. So if you can, let's analyze it out by compensating or statistically analyzing it out. So that's all I got for today. So I guess next week I forgot. Next week I think we got incomplete blocks. I think is where I forgot what it is. No, nested factorial. Okay, yeah, that's interesting too. Yeah, ways to speed it up. Because you can see what we're getting, the kind of problem we got, and I guess this is when factors are nested within one another, and you can't do everything. You can't have this nice little matrix of everybody crosses with everybody. So next week we've got a problem where some of the levels of this factor are only in some of these levels. Oh yeah, that could happen, couldn't it? Because I got some knob set here, and I can only set this knob at certain levels, but if I double that knob, I can't do those other levels or something. How do we deal with that? So you start seeing these, you'll get more and more subtle problems, but it's ways to handle all these problems. So I'm hoping this is good. Again, this book, chapters are quick to read. I would encourage you to read them because there's nice little gems in there, tiny little sentences like the one on page 109, right there in the middle of the page, because I didn't say this, right? I should not let you go before I say it. Our whole data, think about our data in Excel. Remember I made the comment, hey, we had, let's see, where did it go? We had, well, here the data's in our notes, which I just closed. We had the data from that table on page 109, the whole data from example 1, and I made the comment there was no replication, right? So here's our data right here. Yeah. Day 1, day 2, one number at each temperature and pressure combination. There is no replication. But now, so if you're thinking, last week I told you had to have replication to get a random error in that three-way ANOVA. Well, but we had SSE. Where did it come from? Where is it? How did it calculate? What did ANOVA do? Well, you notice in the ANOVA, the way it was laid out, we didn't have any interaction terms, right? I had A and I had B and I had the A. I didn't have the higher order interactions. I didn't have the interactions between the days, and I didn't have the interactions of the days with A and days with B. So those higher order interactions, I've got this one interaction, the A and B interaction. I don't have day with A, day with B, day 1 with day 2. So all of those interactions are what's going into this SSE term. And so that's where that's coming from. And that's a surrogate error term, if you will, replaces the error term you would get if you had the replications. And remember, we did touch on that you could do that. And so that's what's happening here behind the scenes. You didn't kind of know it, but it's worth mentioning because if you step back and thought about it, well, he said you had to have replications to get an SSE, and he showed me with that goofy mistake on the three-way ANOVA that he got the big fat 0 because it didn't have any replication. But here he got SSE when he ran it. Well, it's because it's assuming some replication through those interactions is what it's kind of doing. And so that's where the error term came from. Anyway, and so and the reason I brought that up is that in the chapters there's that little random sentence in there on page 109. Consequently, the random error component in that equation, this equation, is in reality the sum of all the interactions of the blocks with each other. So the extension of that is to include more than 2 factors. So that's little tiny sentence stuck in there telling you where that, because if you're reading through it and you're thinking about it, you go, where did that come from? I didn't have replications. How come it's not a big fat 0? Well, they told you in one teeny little sentence. That's so there's a lot of depth in these chapters. I would read them carefully and think about what they say, because they're short. You can read them in an hour, and then you can go back and read them next week in an hour again. sense after you thought about it. So that's it. That's all I've got for today. That's a good time. I'm letting you out early, right?